This video is about the Jacobian and general changes of variables. Here we're looking at double integrals and triple integrals. And we're talking about changing from rectangular coordinates x and y to some new coordinates u and v, or switching from rectangular coordinates x, y, and z to some new coordinates u, v, and w. We've done this before. Every time you changed from rectangular to polar, you were using a change of variables. So you went from rectangular xy to polar coordinates r and theta, and that was a change of variables. And we also went from rectangular coordinates x, y, and z to cylindrical coordinates r, theta, and z. That was a change of variables. And then lastly, we went from x, y, and z to spherical coordinates, rho, theta, and phi. So that was a change of variables. So these are just three special cases of what we're about to do in this section. We have these special cases because they come up so often, because we often integrate over regions that have symmetry about a point in the xy plane, or we integrate over regions that have symmetry about a line in three-dimensional space, or symmetry about a point in three-dimensional space. So the type of symmetry, is so common that we often switch from x and y or x, y, and z to these coordinate systems. But it turns out you can do this pretty much all the time. If you have a region of integration that you don't want to integrate over, there might be a transformation out there that makes it very simple. All you have to do is let your integral undergo this transformation, and then the new integral is much, much simpler. So that's what this section is about. We'll see some examples of how much nicer everything becomes when we use the Jacobian. But we change for the same reasons that we changed over here. We're going to change from x and y, or x and y and z, to these new variables to do one of two things. We either want to simplify the description of the region of integration, so region R in the xy plane, or that solid region Q in three-dimensional space, or we change variables to simplify the integrand. Maybe the integrand or the integration is difficult because of the form of the integrand, but through a change of variables, we can make it very simple. So, the big picture here is we're trying to make the integration simpler. Or I guess we should say easier. And changing variables will often allow us to do that. Now we change variables in the same way that we changed from rectangular to polar, rectangular to cylindrical, and rectangular to spherical. We need three things whenever we're changing variables. We need new bounds. We had bounds in terms of x and y. Now we need new bounds in terms of u and v if we're doing a double integral, or u, v, and w if we're doing a triple integral. We need a new integrand. So instead of having an integrand in terms of x and y, we need an integrand in terms of u and v. And then we need a new dA. So dA was dx dy before. Now it's not necessarily going to be du dv, but it's going to be something times du dv. And that something is the absolute value of the Jacobian of a transformation. So we'll talk about what that is in a minute. And the same thing is true here, this dx, dy, dz from before. That volume piece is not going to be exactly the same after that transformation. You might need some extra multipliers so that the volume piece in terms of x, y, and z is equal to this volume piece in terms of the new variables. So yeah, that little extra multiplier is called the Jacobian, and that's why this section is called the Jacobian. So let's just look at double integrals first. Most of the problems in this section deal with double integrals. So let's say you've got the double integral over R of f of x, y, dA. So you've got some region over here in the XY plane. Maybe this is R. And you're integrating over it. And that's going to give you the value of that integral. Well, instead of integrating over R, there might be a transformation out there, T, that allows you to take this region R, which looks complicated, and maybe change it into something less complicated. Maybe it becomes a rectangle, something like that. That often happens in these problems. A rectangle S in the UV plane. Now this has to be a one-to-one transformation. That means every XY over here has to correspond to exactly one UV over here. Our book actually uses, well, I don't know if it's our book, a different book uses a transformation T to go from UV to X and Y. But it can really go either way. We could use a transformation T to go from XY to U and V. And then to go backwards, we have T inverse. But again, this has to be a one-to-one transformation. It looks like T takes an XY pair, and the output is a UV pair, where U is a function of X and Y, and V is a function of X and Y. So I replace X and Y with X and Y, those values, and then I get a U value and a V value from that. And T inverse goes the other way. Give me a UV, and I can give you XY back. Here, X has to be a function of U and V, and Y must be a function of U and V. So rather than integrating over R, we're going to integrate over S in the UV plane. And instead of having this integrand in terms of X and Y, we'll have our integrand in terms of U and V. So we'll replace X with whatever it is in terms of U and V, and we'll replace Y with whatever it is in terms of U and V. And this dA, which used to be the X dy, is going to be given by this. It's the absolute value of the Jacobian of xy, of x and y, excuse me, with respect to u and v, times du times dv. That's your new dA. Notice we get this extra factor here. We've done this before. When we switched from rectangular coordinates to polar coordinates, we replaced x with r cosine theta, replaced y with r sine theta, and then dA wasn't dr d theta, it was r dr d theta. There's this little extra factor that was necessary to make the area piece in the UV plane equal to the equivalent area piece in the XY plane. The same thing was true with cylindrical coordinates. That little volume piece, dV, needed an extra r as a factor, and that came from the Jacobian. And in spherical coordinates, later we're going to prove that the Jacobian of this transformation, it goes from x, y, and z to rho theta and phi, gives us rho squared sine of phi. So it's basically what we do. Again, these are the three things we're calculating. We need new bounds, so we need to describe this, we need to take the region R, transform it to a region S, and come up with bounds for the region S in terms of U and V. We need an integrand in terms of U and V, and we need our dA, which is the Jacobian times du dv. Now this Jacobian can be calculated this way. Actually, I think I'll do it right here. This is called the Jacobian of x and y with respect to u and v. It's denoted this way. And it's a determinant. It's a 2 by 2 determinant because we're going from a function of 2 variables, or we're going from 2 variables to 2 different variables. You take the partials of x with respect to u and v in the top row, and the partials of y with respect to u and v go in the bottom row. And then you evaluate this 2 by 2 determinant. You multiply across this diagonal and that diagonal and subtract. Now notice in our formula for the area piece, it's not the Jacobian, it's the absolute value of the Jacobian. The area always has to be positive. Okay. So that's how we do that change of variables in 2D. We're going to go from this to this. To do the change of variables in 3D, we do pretty much the same thing. We're going to go, I'm still going to use R and S. We're going to go from some solid region R in 3-dimensional space to a solid region S in 3-dimensional space. And you're going to replace X with whatever it is in terms of your new variables, V, U, and W. Replace Y with functions of U, V, and W. Replace Z with the appropriate function of U, V, and W. And then dV turns out to be the absolute value of the Jacobian of the transformation times dV in the region S. This is going to be du, dv, dw in some order. Now this Jacobian is very similar to this Jacobian. It just looks a little different because we've got 3 variables. Since we have 3 variables, our determinant will have 3 rows. We take X and we take its partials with respect to U, V, and W. Then we take Y in the second row and take its partials with respect to U, V, and W. And then we take the variable Z and take its partials with respect to U, V, and W. And you evaluate this 3 by 3 determinant in a very similar way to the way you evaluated your cross product determinants, or that determinant form, the cross product. That's going to give you an extra factor. It goes right here. If you do this Jacobian of x, y, and z with respect to rho, theta, and phi, the coordinates for spherical coordinates, this turns out to be, or excuse me, the absolute value of that turns out to be rho squared sine of phi, that extra multiplier that we get whenever we switch from rectangular coordinates to spherical coordinates. Okay, so again, the whole point is to make the integration easier. Sometimes one of the hard parts is to figure out an appropriate transformation that will take us from this region to a region that looks like this. Most of the time, those regions or the transformations are going to be given to you. Let's work some problems. Let's show how this works. I think you're going to like it. I think it's pretty cool. Okay, so let's say you've got a region that looks like this. It's got one corner at 0, 0. Got a parallelogram here. One vertex at x equals 4, y equals 1. Another vertex at x equals 6, y equals 3. One at 2, 2. And then there's another line segment that goes from there to there. So let's say this is the region R, and you want to integrate some function over the region R in the xy plane. Well, that would be a pain in the behind, wouldn't it? Excuse me. The way this is sketched right now, if I were to integrate with respect to, let's say, y first and then x, I would have to separate this into 3 pieces. Then I'd have a top function and a bottom function here, an appropriate top function and bottom function there, and a top function and bottom function there. So I'd end up with 3 different integrals, which wouldn't be too bad. It would just be a lot of work. I would evaluate this integral, and evaluate this integral, and evaluate this integral. And there might be some integrand involved. All I've told you about is the region R that we're integrating over. You might say, but maybe we could switch directions. Instead of integrating with respect to y, why don't we, or y first and then x, why don't we integrate with respect to x first and then y? Well, even so, what would happen if we integrated with respect to x first? Oops, that's not quite right. Well, then I would have to use left functions and right functions. You see, once I get to y equals 1, the right function switches from this line to that line. And then when I get to y equals 2, the left function switches from this line to that line. See, what a pain. I'd have an integral with respect to x first and then y for y between 0 and 1. And then a different integral, a different double integral for y between 1 and 2, and a different double integral for y between 1 and 3. So this is a pain. The way it's sketched right now, this is a pain. I wouldn't want to have to integrate with respect to x or y. But there might be a change of variables that makes this very simple. So to find that change of variables, let's find the equations of these lines and see if we can't see a pattern. Since it's a parallelogram, I'm hoping that I can change this into a rectangle in the UV plane. So let's find the equation of each of these line segments. Well, that's just a line that passes through the origin. It also passes through 2, 2. So I think that's just y equals x. Okay. Over here, I've got a line that passes through 4, 1, and also passes through 6, 3. And I believe that's parallel to this line. So it should have a slope of 1 as well. What's the slope? We go up 2 and over 2. So the slope is still 1. But what's the y-intercept? Where does it cross the y-axis over here? Well, I know that when y equals 1, x has to be 4. So I think 4 minus 3 would give us 1. Make sure that that works for this point as well. If x is 6, 6 minus 3 is 3. X is 4, we've got 4 minus 3, which is 1. So it satisfies both of those. Or you could find this using point slope form or y-intercept form, find the y-intercept. Either way is fine. But you see, we've got y equals x and y equals x minus 3. Now we could also describe this by an equation and this by an equation. Well, that is a line that passes through the origin. We go up 1 and over 4. So the slope is 1/4 x. And this one looks parallel to that. It looks like a parallelogram. Do we go up 1 and over 4 to get this point? Go up 1 to y equals 3 and over 4 to x equals 6? Yes. So it also has a slope of 1/4. When x equals 2, this is going to be 1/2. And I have to have 1/2 plus something equals 2. So I think this has to be 3/2. Let's check it out. If x is 2, I get 1/2 plus 3/2, which is 2. If x is 6, I get 6 over 4, that's 3/2 plus 3/2 is 3. Okay, so those are the equations of my lines. Y equals x minus 3, y equals x, y equals 1/4 x plus 3 over 2, and y equals 1/4 x. Now I could rearrange these just a little bit so that the x and the y are on the same side. I think I want the x first, and I want the x to be positive. So I will add 3 to both sides on this one and subtract y from both sides and switch sides. So this becomes x minus y equals 3. This becomes x minus y equals 0. If I multiply this by 4, I get 4y equals x plus 6. And that I can transform further to x minus 4y equals negative 6. If I multiply this by 4, get that. And then I have x minus 4y equals 0. Okay, now that suggests the transformation. If I let u be x minus y, and I let v be x minus 4y, I think we're going to have constants for our bounds. This line will become u equals 3, and this line will become u equals 0. Here, this line over here becomes, this is v equals negative 6, and this line here, that's a v, it becomes v equals 0. So this region that I didn't want to integrate over because it was going to cause me to evaluate 3 different integrals, whether I integrated with respect to x first and then y, or y first and then x, I can change it. Instead of writing this in terms of x and y over here, rather than integrating over that region, oops, let's do this. I can integrate over this region instead. This is my v-axis, this is my u-axis, and I want u to go from 0 to 3, keep drawing it wrong. Let's do this. U goes from 0 to 3. There we go. And v goes from negative 6 to 0. So that's our region S in the UV plane. Wouldn't you rather integrate over that than integrating over that? That's the beauty of the Jacobian. It did take a lot of work to get from here to here. But once we do all of that work at the beginning, now the integration is going to be really simple over here. So I've got, here's one description of my transformation. I go from x and y to u and v this way. U is x minus y. and v is x minus 4y. Now, I would like the inverse transformation. I would like to know, how do I get from u and v back to x and y? And if you're saying, why would we want to know that? The reason we want to know that is because if I'm integrating over this, I need the Jacobian. So I need to know what x is in terms of u and v, and I need to know what y is in terms of u and v, so that I can compute all of these partial derivatives. So that's the plan. I need to find x in terms of u and v and y in terms of u and v. Right now, I don't have x in terms of u and v, but I have u in terms of x and y and v in terms of x and y. So I need to sort of undo this. I need to do this backwards. So I need to get this as a function of u and v and this as a function of u and v, given that u is equal to x minus y and v is equal to x minus 4y. In order to do that, what you're going to do is you're going to take this and you're going to solve it like you're solving a system of equations. So you're trying to get x by itself as a function of u and v, and you're trying to get y by itself as a function of u and v. I think the easiest one to do first is to solve for y. And the way I'm solving the system of equations for y is just subtracting one equation from the other equation. I'd like to eliminate the x's. So I think I'll just subtract the second equation from the first equation. When I do, I'll get u minus v equals x minus x is 0, 4y minus y is 3y. And then we just solve for y. So y is 1/3 of u minus v, or if you prefer, 1/3 u minus 1/3 v. Similarly, I can take this system of equations and solve for x. That means I need to eliminate the y's somehow. If I'm trying to eliminate y, I need to multiply this first equation by something so that when I'm done and I add these two together, the negative 4y and that term cancel out. So I need this to be a positive 4y. So I'll multiply this top equation by negative 4, and then we'll add them together. We get negative 4u plus v equals negative 4x plus x is negative 3x. Those guys reduce. And we've got that over there. So I would distribute my negative 1/3. And so now I've got x in terms of u and v and y in terms of u and v. And that is my inverse transformation. That takes me from u and v back to x and y. So I can fill in the Jacobian. So this is y. Y is 1/3 u minus 1/3 v, and x is 4/3 u minus 1/3 v. So the Jacobian here would be 4/3 and negative 1/3. Negative 1/3. It's the partial with respect to u for x and the partial with respect to v for x. Down here, partial of y with respect to u is 1/3. Partial of y with respect to v is negative 1/3. So the Jacobian of this transformation turns out to be a negative 4/9 minus a negative, it's going to be plus 1/9. So we get negative 3/9, whoops, which simplifies to negative 1/3. So that's the Jacobian. So if I'm integrating my area piece, the absolute value of the Jacobian times du dv So it turns out to be 1/3 times du dv. That's it. Okay, so that was an example in which we changed this region R into a region S in the xy plane. We also came up with the equations of, we came up with x in terms of u and v and y in terms of u and v by solving a system of equations. And then we found the Jacobian. Okay, so let's do another example. Let's say this is what someone has asked you to do. Someone says this. Evaluate the double integral over R of x plus y times e to the x minus y dA, where R is this region. It's the square, or excuse me, the region bounded by the square with vertices at these locations. It's the interior of a square with these vertices. 4, 0, 6, 2, 4, 4, and 2, 2. Okay. In order to evaluate this, let's sketch the region R. Then we'll sketch or think of an appropriate transformation and sketch that transformed region S. And then we'll come up with a way to describe this double integral in terms of x and y, in terms of a double integral, in terms of some new variables u and v. So always start by sketching. Start with x equals 4, y equals 0, x equals 6, y equals 2, x equals 4, y equals 4, and x equals 2, y equals 2. It doesn't look like a square, it looks like a diamond, but it really is supposed to be a square. This was to scale. That's the region R. It wouldn't be too bad in rectangular coordinates. We just have to do an integral from 2 to 4 and an integral from 4 to 6. Integrate with respect to y first and then x, and then with respect to y first and then x over these two halves of this square. That's a possibility. Or everything might be easier if we describe this line segment and this line segment and this line segment and this line segment differently and change our variables. So first, I notice I've got a line that goes through 2, 2 and 4, 4 in the origin. So that's got to be y equals x. And this one goes through 4, 0 and 6, 2. So we rise 2 and run 2. So that is a line that still has the slope of 1. It's going to have a different y-intercept. A y-intercept that's down here. We know that when x is 4, y is supposed to be 0, so it must be x minus 4 equals y. 4 minus 0 is 4. Or excuse me, yeah, 4 minus 4 is 0, excuse me. And then we've got 6 minus 4 is 2. So this point and this point will satisfy that equation. Okay. And then we've got a line that passes through these 2 points. Now the slope here, we go down 2 and over 2. That's a slope of -1. And I can tell that the y-intercept is 4. And I think that makes sense because we're going back 2, up 2, back 2, up 2. Okay, and then I've got this over here as well. This also has a slope of -1 because we go down 2 and over 2. The question is, what is the y-intercept? Well, when x is 4, we have -4 plus something equals +4. So I think that has to be 8. -4 plus 8 is 4. -6 plus 8, is that +2? It sure is. Okay, so those are the boundaries of my region R. If y equals x, y equals x minus 4. Notice I'm grouping those that have the same slope. It's always good practice. Y equals -x plus 8, and y equals -x plus 4. Now typically, to find the corresponding boundary lines of the region S in the UV plane, we need the x's and y's on one side, and we want constants on the other if we can get them. So I'm going to subtract y from both sides. Over here, I'll subtract y from both sides and add 4 to both sides. On this one, I'll add x to both sides. The same on this one. So I can see if my u is x minus y and my v is x plus y, then this will become u equals 0, u equals 4. If this is my v, I've got v equals 8 and v equals 4. Now you might be saying to yourself, isn't it because it's a parallelogram? Yes, you're right. We'll look at one that's not a parallelogram in just a bit. But u goes from 0 to 4, and v goes from 4 to 8. This is not to scale. But that's our region S in the UV plane. I'd much rather integrate over here than integrate over here. There's 2 double integrals that I have to evaluate here, and y goes from a function to a function in both cases. Here I'm integrating over a rectangle. The bounds are constant. U goes from 0 to 4, and v goes from 4 to 8. It's nice, easy integration there. Okay, so we've sketched the region S. We know the new bounds. And what else do we need? We need a new integrand, and we need a new dA. So we did our first part was the new bounds. And the way we did that was we sketched, or we found the equations of each of those boundary curves, and then we tried to write them in such a way that we saw that same expression twice in 2 equations. I had an x minus y in this equation and an x minus y in this equation. That gave me 2 equations for u. And then the same over here. I had an x plus y equals a constant, x plus y equals a constant, so I had 2 equations for x plus y. And I sketched these bounds here, and I stated them. So that gave us our region S. Okay, now we need the new integrand. And the integrand of the original function may have given us a tip of what we should use for our u and v. F of xy was x plus y times e to the x minus y. Well, remember what we chose for u and v. U was x minus y, so that's e to the u. And v was x plus y, so that's a v. So now I've got my new integrand in terms of u and v. I'm putting a little asterisk there because that f is not the same as that f. But these are the same. I've just written that this new integrand in terms of u and v instead of x and y. Like this quantity is equal to this quantity under the transformation. But the function f is not equal to that function f, so I put a little f star there. Okay. So we've got new bounds, we've got a new integrand. The last thing we need is a new dA. And remember what you need for dA. dA is the absolute value of the Jacobian times du dv or dv du, either one is fine. It's our modified area, because the area pieces over here are not equivalent to the area pieces over here. So you have to figure out what that equivalence is. This requires calculating the Jacobian, which is actually pretty simple. The hard part, though, is finding x in terms of u and v, so you can take those partials, and finding y in terms of v, so you can u and v, so we can take those partials. It's not that hard, but there is a step required. In order to get x and y in terms of u and v, we have to use these equations from earlier. We know what u is in terms of x and y, and we know what v is in terms of x and y, but we need it the other way around. So we need to solve this system of equations, u equals x minus y, and v equals x plus y, for x as a function of u and v, and y as a function of u and v. I know a lot of students look at this and they're like, oh my goodness, there are too many variables. Try not to think of it that way. When you're looking at this system of equations, you want to treat u and v the way you would treat constants. Solve this the same way you would solve x minus y equals 4 and x plus y equals 7. U and v, you're just going to treat them like constants, and you're going to eliminate variables the same way that you would eliminate variables when solving a system of equations. Okay, so let's solve for x first. I can see it's pretty easy to solve for x, because if I add these equations together, my y's are immediately eliminated. I'll call this equation 1 and this equation 2. Let's do equation 1 plus equation 2. That's going to give me u plus v equals 2x. So then I'll solve for x by dividing both sides by 2. So I have 1/2 u plus 1/2 v. Oh, actually, I'll do this. And then to get y by itself, let's multiply this top equation by -1. So the top equation would become -u equals -x plus y. The bottom equation is still x plus y equals v. And now when we add them together, that multiplying that top equation by -1 allows us to eliminate the x's. This -x plus x will give me 0. So when I add these together now, I've got -u plus v equals 2y. So divide by 2. Now you've got -1/2 u plus 1/2 v. Okay, and now that you have x in terms of u and v and y in terms of u and v, it's easy to compute the partials. Partial of x with respect to u is just 1/2. Partial of x with respect to v is also 1/2. Partial of y with respect to u is -1/2. Partial of y with respect to v is +1/2. So we'll put those in our matrix up here, or excuse me, our 2x2 determinant. So 1/2, 1/2, -1/2, and 1/2. And then we evaluate. So we're gonna have 1/4 minus a negative, that's gonna be +1/4. 1/4 plus 1/4 is 2/4, which is 1/2. So this becomes 1/2 times du dv. That's our area piece. Turns out the dx dy over here is equal to 1/2 of du dv over here. Okay, now I think we've got everything we need. We needed new bounds, we've got them. We needed a new integrand, that's right here, we have that. And we need a new dA, and that's right there. So let's put all the pieces together to state and then evaluate our integral. So I have the double integral over R of x plus y times e to the x minus y dA is the double integral over S. Well, u goes from 0 to 4 when v goes from 4 to 8. Of this transformed becomes v times e to the u. The new dA is 1/2, and we're integrating with respect to u first because of the order I wrote those over there, so that's du dv. So remember, you need those three things: new bounds, new integrand, and a new dA. Isn't that nice? Nice and easy. Now let's integrate with respect to u first and then v. We're going to start on the inside and work our way out. 1/2 is a constant, v is a constant. Antiderivative of e to the u with respect to u is e to the u. We evaluate from u equals 0 to u equals 4. When u equals 4, we've got 1/2 v times e to the 4th. When u equals 0, we're subtracting e to the 0, so that's a 1. Integrate that with respect to v. So 1/2 is a constant, e to the 4th minus 1 is a constant. The antiderivative of v with respect to v is 1/2 v squared. Add 1 to the exponent, divide by the new exponent, and then you evaluate from v equals 4 to v equals 8. So we'll have 1/4 e to the 4th minus 1 times the quantity 8 squared minus 4 squared. So you have 1/4 times e to the 4th minus 1 times 64 minus 16. Excuse me. So you've got e to the 4th minus 1. 64 divided by 4 is 16. 16 divided by 4 is 4. So I end up with 12 times e to the 4th minus 1. That's my answer. But again, what do you need? New bounds, new integrand, new dA. Both of the examples that we worked in this video involved taking a parallelogram and creating a rectangle. I'm going to do 2 more examples for you that don't involve parallelograms so that you can see how something like this might change in the UV plane in a way that doesn't necessarily give you a bunch of constants for your bounds in the UV plane.